If we look at this, the graph of the cosine function, so this is the graph of y equal cosine x, it is clear that the function is cannot be one-to-one function because for example the horizontal line test is not satisfied. Okay, so if you just imagine a line, okay, so you see it cross at the same for the same y. We have several x that have the same image, so it is not one-to-one function. It's not one. Similarly, the sine function also, is not, and tangent function also is not one-to-one function. So, however, we are interested to define one-to-one inverse functions for trigonometric function by restricting the domain. For example, here, for the case of the cosine function, so I can see that if I work from 0 to pi, okay, from 0 here to pi on this interval, my function here is decreasing. Okay, so here is the restriction here is the graph I'm considering. So here cosine is monotone, is decreasing, so it will be one-to-one function. And for this restriction, we will define a new function, which is the inverse function that we will call arc cosine. Okay, so this is what we will specify in this section. We will define the arcsine. How we will restrict the graph of the sine function to the following interval. Okay, x, y. So we will restrict it to minus pi over 2 to pi over 2. At pi over 2, the sine function takes the value 1. At minus pi over 2, it takes the value minus 1. Okay, and we know that the function is increasing. Okay, so let's just y equals sine x. Y prime is cosine x. So for, yes, it is increasing the trigonometrical circle, unit circle. It helps to see the sign, to read the sign. Okay, sine. So this is the sine x. I read sine x, and here I'm reading cosine. No, the inverse. I'm reading here cosine of the angle. Okay, if I have an angle here, an angle of x, so what I read here is my cosine of x. What I read here, okay, this point is the sine x. Okay, so that's why we call the sine axis and cosine axis here. Okay, so what I'm doing here, I'm hesitating about the convexity, that's why I'm deriving again here sine x. So for x between minus pi over 2, here is minus pi over 2, here is 0, and here is pi over 2. Here it's pi. Okay, so from minus pi over 2 to 0, sine is negative. Any angle here, its projection will give me here something negative. So negative with negative is positive, so it is convex. So the graph here will be something convex, something like that. Okay, now what about for x between 0 and pi over 2, the angle is here, so the projection will give me a sign that is positive. Sine positive with minus negative, so I have then concave arc. and then so 0 is an inflection point. So here is my graph. Now I'm sure that it behaves like that, and they have, of course, here horizontal tangent. They have horizontal tangent here, horizontal tangent. So the shape is is like that. Let's do it better. So we'll have something like that. Okay, here it is. Okay. Yes, so is 1 to 1. So I can say y equals sine x, okay, is with x restricted to belong to minus pi over 2 to pi over 2 is equivalent to say that x is arcsine, the inverse function arcsine of y, which we denote also sine minus 1 x y. Okay, with y here belongs, so y belongs to minus 1 1. Okay, so here is my new function. Okay, we can deduce, of course, okay, we can deduce properties of the arctan function just from the ones we know of the sine function. So let's so keep this one. So this box is important. Now let's deduce monotony and other informations. Okay, so we will have, let's just compare sine x. So defined restricted to minus pi over 2, pi over 2. We said it is an increasing function, taking values minus 1 to 1. Then from this table I can deduce what is happening for the arcsine function. Arcsine function then is still increasing function. Okay, remember, it's the derivative of the inverse function is 1 over the derivative of the original function. So the sign depends on the original. Here it's positive, the derivative, so here it will be increasing also. Now the range is will be the domain of the new function. So from minus 1 to 1, and takes the values, corresponding values, minus pi over 2, pi over 2. So like that, we know already some particular values of arcsine of minus 1 will be minus pi over 2, arcsine of 1 is pi over 2. What about the derivative we said? So the derivative of the arcsine, dx of, maybe I should work on it first and show directly how we can find it. So we said, let's set y equal arcsine minus 1 of x. So I can, so this gives me then the equivalence sine y as a function of x is x. And then I can derive, then if you derive a composite function, you will have cosine of y of x times everything y prime of x equal 1. Then y prime of x is 1 over cosine of y of x. Okay, so now let's express everything in x. So yx, so it's related, yes, is connected here. So I know something. So what can I say here? Cosine of y. Yes, there is a relationship between sine and cosine. We have always cosine y square plus sine of y square. Sorry, cosine y to power 2 equal 1. Okay, that, so fine. Yes, but then okay, so from here, so we have cosine y square will be 1 minus sine y square, but sine of y, that means y minus sine. What is our y? Is sine minus y. So this is the inverse function. So it will give me 1 minus x2. So from here, I can deduce that cosine y, but now something else to pay attention to is when my x is between minus pi over 2 and minus pi over 2 to pi over 2, the cosine is always positive. Okay, so because we have x between minus pi over 2 and pi over 2, then cosine cosine of what is it, cosine of, because y is between the, sorry, y is between, because y here the angle is y, then cosine of y is positive. Okay, so that from here we can deduce then cosine y is the positive root, okay, the square root of 1 minus x2, which gives us now the new formula of the derivative of the new function, okay, of arc sine x is nothing than 1 square root of 1 minus x2. So it is defined by function that we know to manipulate. And since we have this, that means we deduce immediately that an antiderivative of this function, okay, is now well known arc sine of x plus a constant. So you see, we have two new things now here: a derivative of a new function and a new antiderivative. Great. Okay, so yes, knowing that, so we can have several different questions about these new combined with new functions. Many questions can be of interest. Okay, limits, continuity, differentiability, many things. Okay, let's now define the arc cosine function in similar way. So this time I will go faster. So I will just show my restriction. So I will restrict my definition to this interval. So I see it here. We said from 0 to pi. 0 to pi. Okay. And at 0 it takes the value 1. So it does something. At pi over 2 it takes the value 0 and passes. So we have 1 point here, we have another point here, and pi, at pi we have minus 1. So I have another point here. Okay, and yes, we have then the following shape. So we have something like that. And we define our new function arc cosine as, so we will say that y equal cosine y will be, let's use another color, blue one. So y equal arc cosine of x, where my x here is between, with x between 0 and pi, if and only if x x is the cosine of y, with y between minus 1 and 1. Okay, so this is the characterization of our new function. Okay. Yes, we can deduce immediately yes, the images like we did here, but maybe it's not necessary. So the derivative, I will just give the derivative. Okay, yes, maybe monotony, it's a good idea, monotony. So for cosine function, here we are restricted to work So this is y equal cosine x. Yes, I didn't speak about the graph of the arcosine, but we know that we can deduce it by symmetry with respect of the line y equal x. Okay, so y equal x, and you can deduce something like that. Okay, for the arcsine. Okay, so we said we work on the interval 0 from 0 to pi, and our function is decreasing, and sorry, let's do it better, is decreasing. At pi takes the value -1 and here 1, at 0 at pi over 2 takes the value 0. So here for the arcsine, arc cosine, arc cosine x is defined from -1 to 1. Okay, is a decreasing function, takes the value pi at 0, so takes the angle pi over 2, and 1 is 0. Okay, so this is a decreasing function. We can show that, we can check that the derivative of this function, so I will give just the formula, the dx of the arc cosine x is this time is -1 over square root of 1 minus x2. Okay, for x between -1 and 1. Here also, yes, we need to specify the derivability. Okay, -1 and 1. Okay, it's not differentiable at 1 and -1. Great, so let's okay, we have then our box, and now yes, a remark. Let's do this remark from here. Remark. So we notice that the derivative, okay, derivative of arc cosine x is the opposite of the derivative of the arcsine of x. Therefore, the derivative, if you move the other term and use the operation on differentiation, you have arc cosine x plus arcsine x equals 0 for x between -1 and 1 over an interval. Okay, over the interval -1 and 1. So we know that then, because these two functions are differentiable, we know theorems that says that the inverse function of a differentiable function is differentiable, then it is a constant. Arc cosine x plus arc sine x is a constant c. To identify c, choose. So now if you would choose, so let's choose x equal 1. Yes, choosing x equal 1 gives us arc cosine 1 is 0, so then we have 0 plus 1 equals c. There's arc no, equal pi over 2 here, so c is pi over 2. Okay, so we have this formula. Okay, this equality. That's why so it's justified now. Oh, now the last function is the inverse for the tangent function. Tangent function also is periodic function. It's not cannot be one-to-one, but its restriction will be will define new function is one-to-one, and the inverse gives us the arctangent function. So here it is. Here is my graph, my restriction. I want to show the restriction. So the restriction we will consider is, we know the tangent, you remember, tangent x is sine x over cosine x. So it's not defined on minus pi over 2, pi over 2, plus pi, and all the points. So we will restrict minus pi over 2 and pi over 2. These are vertical asymptotes for our function, and we know the tangent function behave like that. Okay, it's like x3. Okay, and so it's an increasing function. We know even its derivative. Remember, the derivative of tangent function is 1 over cosine x squared, which is positive. So increasing, it's 1 over this interval. Okay, so we define. So let's we define the new function. So y equal. So let's do it here. So y equal arctangent tangent x with x between minus pi over 2, no, x in r, no, x be, no, so maybe I'm hesitating, so just let's start then the table first. So x is restricted to be from minus pi over 2 pi over 2, and my tangent function is increasing function. So it takes plus infinity minus infinity at the asymptotes. So the inverse function x arctangent x will be defined everywhere. Okay, and it will be an increasing function, and from minus pi over 2 pi over 2, so it has two horizontal asymptotes. So here, yes, x belongs to r, and equivalent to say that x is tangent of y, with y between minus pi over 2 and pi over 2. Like that, we have all the informations needed. Okay. Yes, so once we have this, we need to define, yes, to check the derivative. The derivative, yes, so, yes, here I didn't mention, but we know, yes, the antiderivative of the arctangent, I need to add it maybe, arcosine is minus, or, so there is just a difference from here. Okay, so maybe I can, so let's continue in the same idea here. The x of the tangent arctangent x, we show that it's 1 over 1 plus x2. Therefore, an antiderivative of 1 over 1 plus x2 dx is the arctangent function plus a constant. Yes, here I want to add just a remark that antiderivative of minus 1 over square root 1 minus x2 dx is also r cosine x plus a constant. So we have the three new relations. So with that, so any questions now related to the three functions combined with the ones you know can be addressed and discussed.